Greetings and welcome to Distillate. In the previous class, we had studied about a few basic variables in thermodynamics, which included heat, internal energy, work done. Then we categorized work done into two parts. One was internal and one was external work done. Right? So internal work done is basically due to internal expansion or compression of the gas itself. All right. So if that happens, then in that case, the work done is basically internal in nature. And when we talk about external work done, then external work done is basically any energy that is transferred to the system, which is not because of change in temperature or which is not because of temperature difference. That is basically counted as an external work. All right. So this is there. Then we talked about heat. Heat is basically energy transferred because of temperature difference, right? And then we discussed about internal energy. So internal energy is the energy that is possessed by a system due to its the translational, rotational, and vibrational motion of its molecules, right? That's what we studied about, these three quantities. Then we discussed about thermodynamic processes. So in thermodynamic processes, we studied about four major processes. We studied about isobaric, isochoric, isothermal, and adiabatic. So once again, I'll just draw the table which I gave you people in the previous class. So first of all, we have the isochoric process. So in the isochoric process, you have a equation of state for an isochoric processes. V is equal to constant, which gives us P1 by T1 is equal to P2 by T2, right? That is the equation of state for an isochoric process. Then when we talk about an isochoric process, then first law is applied to an isochoric process as dW is equal to 0. Therefore, you get dQ is equal to du. All right, that is your first law for an isochoric process. All right, so that is how you basically deal with an isochoric process. So here you have volume constant. All right, here you have the volume constant. Then we have the next thing, that is our isobaric process. So an isobaric process is basically where your pressure is held constant. All right, where your pressure is held constant. So over here, you will have the equation of state as V1 by T1 is equal to V2 by T2. And over here, there is no as such difference. So you'll directly get dQ is equal to du plus dW, which is du plus minus PdV, depending on whether it is expansion or compression. All right. Then the third process that we studied about was an isothermal process. So an isothermal process, you have temperature constant. So if temperature is constant, then your equation of state becomes P1 V1 is equal to P2 V2. And we evaluated the first law of thermodynamics as du equals to 0. So you'll get dQ is equal to dW for this one. And the fourth one was adiabatic process. The fourth one was adiabatic process. So for an adiabatic process, you have heat transferred. There is no heat transfer. So your equation of state is P1 V1 to the power gamma is equal to P2 V2 to the power gamma, where gamma is equal to specific heat capacity at constant pressure upon heat capacity at constant volume. All right. And in the previous video, I think I wrote du is equal to dW. I think I wrote this, but it's actually du equal to minus dW for an adiabatic process. So please make this correction if you people have written it wrongly from the previous video. It's going to be PU equals to minus dW. All right. So that's there. And then there's one more thing. Yeah. So for each of these processes, you can calculate work done, right? You can calculate work done by or on the system, right? So work done in an isochoric process is 0, right? Because there is no change in internal energy. No change in volume. Therefore, work done is 0. For an isobaric process, you can simply get dW is equal to PdV, or at least you can get mod dW is equal to PdV, where dV is basically the difference between the volumes, right? Bigger volume and smaller volume. And then if it is expanding, if it is an expansion process, then in that case, since for an expansion process, the work is sent out of the system, right? Therefore, it is going to be positive. And for a compression process, it is going to be negative, right? And then you have another thing for isothermal process. We evaluated work done as RT ln bigger volume by smaller volume. All right. And that is also equal to RT ln bigger pressure by smaller pressure, because corresponding to smaller volume, you have the bigger pressure. All right. So this is going to be mod W, and then again, depending on expansion or compression, you will get the work done. And finally, work done for an adiabatic process, we calculated it as P1 V1 minus P2 V2 upon gamma minus 1, right? That is what we calculated. And this can also be simply written as R times T1 minus T2 upon gamma minus 1, where T1 has to be the greater temperature and T2 has to be the smaller temperature. Then again, depending on whether it is expansion or compression, you're going to have work positive or negative. So this is the basic information that I provided in the previous class. So with this, with all the information about PV diagrams, about different thermodynamic processes, let's go on and solve a few problems. So let us see example number 1. An ideal gas is in state A, where P is equal to 1 bar and V is equal to 1 liter. All right. From here, it moves to state B through an isochoric process. Isochoric process means the volume is constant. At state B, its pressure is 12 bar. All right. In an isobaric process, from state B, it moves to state C, where the gas occupies 6 liters. All right. And from here, it moves to state D along an isochoric process. And then from here back to state A along an isobaric process. So it's basically a combination of isochoric and an isobaric process. So draw a PV diagram for this process and calculate the overall work done, change in internal energy, and heat transfer. So let's see. So to draw a PV diagram, we are first going to have pressure versus volume, PV. Right, this is my PV. All right. Now, first of all, go back to the question and identify wherever they have mentioned any values for pressure or volume. So pressure, they have mentioned 1 bar and 12 bar. So go and mention it over here. So this is 1 bar, this is 12 bar. Okay. And then we'll again see for volume. So volume, it's 1 liter and 6 liter. So 1 liter and 6 liter. Okay, something like that. So this is my 12 bar. This is 1 bar. This is 1 liter. And this is 6 liter. Okay, that is the condition. Okay. Now what we are going to do is we are going to draw the PV diagram. All right. So initially it is in the state P equals to 1 bar and V equals to 1 liter. So 1 bar and 1 liter, it's somewhere here. All right. So your state A is over here. Okay. This is your state A. Okay. From this state, it is moving to state B through an isobaric process. So it's isobaric implies volume remains constant. A to B is isobaric, therefore its volume is going to be constant. So it is going to move along this green line, the vertical green line. All right, it's going to move vertically. Right. Now, to identify where it moves, we have to see the final pressure. So final pressure is 12 bar. So definitely it's going to go up. Right. So it's going to go up. So here it is going up and it has come to 12 bar where it's where it is at state B. All right. And we are going to obviously give a direction from which direction to which direction has it gone. So it has gone from A to B. So we are going to make an arrow over it. All right. This is quite basic, but okay, still just understand. Then in state B, so we'll also keep on mentioning the properties. So we'll have state. We'll have state. We have pressure and we have its volume. All right. So now state A, B, C, and D. Okay. Then pressure in state A was 1 bar. Pressure volume in state was 1 liter. State A, it was 1 liter. Then pressure in state B was 12 bar and volume in state B was 1 liter. All right. Then we move on to further go with our process. So from in an isobaric process from state B. So it's isobaric, so it has to move horizontally. From state B, it has to move horizontally. It moves to state C where it occupies 6 liters. So it will move horizontally and it will move till a point where its volume is 6 liters. So here this is going to be state C. So we are going to take it till here. Okay. And then from here it moves to state D along an isobaric process. All right. So state C, from state C it is going to move 12 bar and 6 liter. From state C it is going to move to state D. Okay. But we don't know whether its volume is going to be sorry, it's an isobaric process. So therefore it has to move vertically, right? So it will either move up or it will move down. We don't know. And we also don't know what pressure is it going to be in state D. So we don't know the pressure of state D. We have no idea. All right. So neither do we know pressure nor do we know volume of state D. All right. So now what we are going to do, we are going to go further. From here it moves to state B along an isobaric process, and then from here back to state A along an isobaric process. So from D it goes to A along an isobaric process. So it is moving from D to A in an isobaric process. Therefore, implies the pressure is going to be constant. And if the pressure is constant, that means pressure at A is going to be equal to pressure at T. So what is pressure at A? Pressure at A is 1 bar. So here also it's going to be 1 bar. All right. So that means we have located state D, that is over here. Hence, its volume is going to be 6 liters. Actually, volume we already knew because volume of C is going to be equal to volume of D. It's an isochoric process, right? So from C, it will go to D, and then from D, it is going to go back to state A. Okay, so this type of a process in which a gas starts to move from its initial state, it travels a path and then returns back to its initial state. That means in a process where the final state is same as the initial state. Final state is same as the initial state. This kind of a process is known as a cyclic process. All right, remember this thing. This kind of a process is known as a cyclic process. And for a cyclic process, the cyclic integral of state properties is 0. I'll just explain what is the cyclic integral. Cyclic integral is basically the sum of all the changes within the properties, sum of all the changes within the properties over this particular cycle. So basically over here, if I'll take one state property, let's say internal energy. Internal energy is a state property. So if I evaluate the cyclic integral, the cyclic integral is going to be the change in internal energy about AB plus change in internal energy about BC plus change in internal energy about CD, and finally change in internal energy about D. All right, altogether this is going to be equal to 0. This is a cyclic process. All right, this cyclic integral can be simplified in this manner. All right, so we basically have to take an integral over the entire region. All right, you have to take an integral over the entire region. So cyclic integral of all the state properties is going to be 0. Therefore, you can say that for a cyclic process, delta of state property. Delta state property means a state property in the final state minus state property in the initial state. It is going to be equal to 0. Okay, this is a very important result for a cyclic process. All right, so in a cyclic process, you can always say that throughout the cycle, for the entire cycle, not for individual processes within the cycle, for the entire cycle as a whole, the integral of du is equal to 0, and also even du is equal to 0. There is no change in the internal energy in the entire cycle. Individual processes, there may be a change, but in the entire cycle, there won't be a change. So this is a very important result that you get for a cyclic process, right? Now, once we are done with this, let's do our further calculations. All right, so let's draw a PV diagram that we have done and calculate the overall work done, change in internal energy and heat transfer. So since it is a cyclic process, since A, B, C, D, A is a cyclic process, therefore integral du, that is delta u, is going to be equal to 0. Very important. Okay, du is equal to 0. All right, keep this in mind. Okay, now once we have found out about this, we know that dq is equal to dw by first law. All right, so for a cycle, dq is going to be equal to dw. Okay, dq for a cycle is equal to dw for a cycle. All right, so that means whatever heat is added to the system is used by the system to do work. All right, if this is my system, and I am adding heat to the system, overall I have added some heat, So all of that heat would be used to do work. All right, all of it would be used to do work. Clear? So that is there with a cycle. All right. So we only need to find out the work done. All right. So let's see how to find out the work done. So work done is very easy. We know that work done is integral PdV, right? That means, or I'll actually say mod of work done is integral PdV from V1 to V2. Or we can say the area under the curve over the process, right? Area under the curve over the process. All right. So now let's see. Since we have to find the work done for the entire process, so work done for the entire process is going to be equal to work done in A to B plus work done in B to C plus work done in C to D plus work done in D to A. All right, that is it. Now, let's go back to our PV diagram. AB is an isochoric process. So for an isochoric process, work done is always 0. All right, so this we have got as 0. Then we move on to B to C. Now, if you see B to C is expansion. It is moving from 1 liter to 6 liters. So it's an isobaric expansion. So therefore, work done is going to be positive. All right, work done is going to be positive. And what is the magnitude of work done? Magnitude of work done is basically the area under the curve BC. So area under the curve BC basically involves the entire thing. This entire thing. So all of this comes under BC. Okay, so this is my area under the curve for BC. All right, this is my area under the curve for BC. Then what? So the area under the curve would be, since this is a rectangle, so length, that is 12 into breadth, that is 6 minus 1. Or you can simply use P delta V for an isobaric process. So this is going to be 12 into 6 minus 1. 12 into 6 minus 1. And positive because here work is done in expansion. Here it is expanding. Then C to D is again an isochoric process. So here C to D, it is going to be 0. All right. And finally, D to A. D to A is this one. So we have to find the area under the curve D to A. DA, that is this area. This area we have to find. Okay. So this area is basically, again, it's a rectangle. So length into breadth, that is 6 minus 1. Or you can say the P delta. All right. So this is the magnitude of work done. But over here, if you see, it is moving from 6 to 1. So it is basically work done in compression. So that is why its sign is going to be negative. Its sign is going to be negative. So 1 into 6 minus 1. All right. That is how you get it. So it is going to be 12 into 6 minus 6. All right. So from here, we'll get 12 6. All right. So this would give us, this is the work. Actually not joule, it's bar liter. We have not yet converted this. Okay. Hope you are clear. Now let's see what unit it actually is. So 1 bar is 10 to the power 5 Pascal. And 1 liter is 10 to the power minus 3 meters. So when we find 1 bar liter, that is actually equals to 10 to the power 5 into 10 to the power minus 3 Pascal meter cube. So that is 100. Pascal meter cube. That is 100 joules. So 1 bar liter is equal to 100 joules. So this becomes 6600 joule, which can also be written as 6.6 kilojoules. All right. So this is your work done. All right. This is your overall work done. Okay. And the heat transfer. Since dq is equal to dw, therefore overall heat transferred is 6.6 kilojoule. So this basically means that I am transferring 6.6 kilojoules of heat to my system, and this system is doing work equivalent to 6.6 kilojoules. All right. So that is the basic meaning of this, of the first law for this particular process. All right. So hope you are clear as to how to make the block diagram, what are the state properties, how do they affect, how are they changed while we are dealing with a cyclic process, how to calculate work done for a cyclic process, right? Or in general, how to calculate work done from PV diagram. So hopefully you're clear with these concepts, right? So once we are done with this, let's go on to example number 2. So an ideal gas has the following equilibrium states: state A, B, and C. They have given us different values. So see, they have also given internal energy for each of the states. So from here, we can actually get the fact that internal energy is also a state property. So even internal energy can be written along with the state. We cannot write Q or W because they are not state properties, but we can definitely write U or pressure, volume, temperature, of course, for a particular state. All right. So if the system moves from A to B, B to C, and then C to A, and C to A is an isotherm, determine the heat transferred to or from the system in each of the state transitions, work done by or on the system in each of the state transitions, and finally change in internal energy for each of the state transitions. So once again, the first step for solving a thermodynamics problem is to draw a PV diagram. It's very easy. It becomes very easy when we draw a PV diagram. So let's draw a PV diagram for this case. Pressure is in Pascal, volume is in meter cube. Okay. So pressure is 20 Pascal, 10 Pascal. So 10 Pascal will be somewhere here, and 20 Pascal we can put somewhere here. Volume is 1 meter cube, whatever is given for now. And then they have told you that at 20,1, that is over here. I'll just draw proper lines. Okay, now the state A has 20 Pascal and 1 meter cube. So state A, it can be located somewhere here. So state A can be somewhere here. State B, they have given 10,1, so 10 Pascal and 1 Pascal. So here we can have B. All right. So they are saying that it moves from A to B, B to C, and then C to A. So we'll move it from A to B first of all. What all information we have, we'll use it. Okay. And then they're also saying that state C is at 10 Pascal. So basically it would either be here or it would be here. That means it has to move horizontally, right? It has to move horizontally. Okay. Then they have given that pressure, sorry, C to A is an isotherm. So since C to A is an isotherm, So isotherm means the PV diagram for an isothermal process. So that means that for an isotherm, this is going to be your initial state, and this is going to be the final state for the isothermal process that is going to take place, right? So therefore we can use the equation of state for isothermal process, right? We can use the equation of state for isothermal process. So that is going to be equal to PCVC is equal to PAVA. Now they have given us PC as 10, VC we don't know. So 10 into VC is equal to PA we know it's 20 and VA we know it is 1. So from here you get VC is equal to 2 liter, right? VC is equal to 2 liter, right? So from here we get VC over here, 2 liter. This is not in meter cube, this is in liter. Okay. So this is my VC. So once I have got the pressure for C, PC as 10 Pascal. We have PC equals to 10 Pascal. And we have VC is equal to 2 liter. So 10 Pascal, 2 liter. So C would be somewhere here. So this is going to be C. B to C. All right. And then C to A is an isotherm. And for an isothermal process, if you remember, the curve is something like this. Curve is something like this. So it is going to be, I've not drawn it very nicely, but hopefully people have understood what I'm trying to say, right? It is going to be something like this. So this is my PV diagram. All right, this is my PV diagram. So first step for these types of problems is to complete the PV diagram. Once you complete the PV diagram, then solving the problem is easier. All right. For now, let me just write down everything. Over here, this is an isochoric process. Over here, it is an isobaric process. Over here, it is an isothermal process. All right. That is what we know. Okay. Now, we have to find the work done, heat transferred, and internal energy. Also, we have internal energy here at state A as 150 joules, UA as 150 joules, then UB is 100 joules. Okay, UB is 100 joules. Also, since B to C is an isothermal process, sorry, not B to C, C to A is an isothermal process. Therefore, for C to A, you have du from C to A is equal to 0 because it's an isothermal process and internal energy depends on temperature. So for this, the internal energy is going to be the same because the temperature is the same. So since du is 0, that means UA minus UC is 0, which means UA is equal to UC is equal to 150 joules. So UC over here, you will get as 150 joules. Okay. So keep this with you. All right. So once we have done that, let's go ahead and find work done. First of all, let's find work done for each process. So work done in A to B. Work done in A to B is 0 because it's an isochoric process. Then work done in B to C is basically P into delta V. It's meter cube, sorry. I don't know why I have written liter. It's meter cube. This is meter cube. All right. Sorry. So now we have B to C is an expansion process, right? B to C is an isobaric expansion. So work done is going to be positive and it is going to be equal to 10, that is P, into delta V, that is 2 minus 1. So 10 into 2 minus 1, that is 10 joules. This is Pascal, this is meter cube. So Pascal meter cube becomes joule. All right. And then finally, WC to A. Now this is isothermal compression, right? This is isothermal compression. So therefore, you'll get WCA as minus R into T into minus R into T into ln V2, ln bigger volume minus smaller volume. So ln 2 by 1, right? So ln 2 by 1. Now, how are we going to find out this T? So this T is basically PAVA by R, because by ideal gas equation, we know that PAVA is equal to NaRTA. All right. And let's make an assumption of 1 mole of gas, right? So in that case, you'll get Na equals to 1. Okay, Na equals to 1. All right. So once that is there, then we'll get TA is equal to PAVA by R. And it can also be written as PCVC by R, because P1V1, PAVA is equal to PCVC over here, right? So we are going to put that over here. So you'll get minus R into PAVA by R ln 2. All right. So PAVA is basically 20 into 1. So that is minus 20 ln 2. That is work done in C to A. All right. So on this basis, we can find out the work done. All right. So that is equal to 13 minus 13.863 joules. All right. That is my work done in C2. All right. That is work done in C2. So the net work done is basically summation of all these processes, work done in all these processes. So it is going to be minus 3.863 joules. All right. Minus 3.863 joules. Then let's consider one process at a time. Okay. So when we consider A to B, then we have W0. All right. Then du is basically u final minus u initial. So ub is given to be 100, ua is 150. So 100 minus 150, which gives us minus 50 joules. And then by first law, we'll get dq equals to du, that is minus 50 joules. So minus 50 joules means in this process, you are losing a heat of 50 joules. Okay, heat out of this process during A to B is 50 joules. All right. Then we'll take the next state, that is B to C. So in B to C, your work done is plus 10 joules. That means work has been extracted. All right. And internal energy, du, is basically u final minus u initial. So uc we have seen 150. So it's going to be 150 minus ub is 100. So we will get 50 joules. That is my internal energy. So you'll get dq is equal to du plus dw. That is 50 plus 10. That is 60 joules. All right. So this plus 60 joules has been supplied. 60 joules has been supplied. 60 joules of heat has been added to the system. All right. And then let's take C to A. So when we take it from C to A, then work done in C to A is minus 13.863 joules. Okay. Since C to A is an isothermal process, therefore du is equal to 0. Hence, by first law, we'll have dq equals to dw, that is minus 13.863 joules. Right? So, over here, again, 13.863 joules of heat has been extracted. Now remember, over here work done is negative. That means work has been added to the system. All right, so overall it is balanced. Whatever work has been added, the same amount of work has been, the same amount of energy has been extracted using heat. All right, so dq is equal to dw is valid over it. So all over, you people can calculate what is the work done, right? So now for calculating q net, you can either add all of them, all the heats that you have calculated so far, or you can simply put it equals to w, because for a cyclic process, this is a cyclic process, and for a cyclic process, the net heat gained or lost is equal to net heat and net work done by or on the system. All right. So once we're done with this, let's move on to the next example. So go ahead, pause the video and try to solve this problem yourself. Hope you could solve this problem yourself. If you could not, then let's see how it's done. A system consisting of gas confined in a cylinder is undergoing the following series of processes before it is brought back to its initial conditions. First, it is going through a constant pressure process where it receives 50 joules of work and gives up 25 joules of heat. So in step 1, if this is my system, I'll not draw entire diagram, just a block. All right, this is my system. So it receives 50 joules of work and it gives up 25 joules of heat. Okay. Then we are going to say that step 2, a constant volume process where it receives 75 joule of heat. All right. So that is step 2, where it is a constant volume process. So it receives 25 joules of heat. 25 joules, 75 joules. Sorry. So it receives 75 joules of heat and it does not do any work because it's an isobaric process. And step 3 is an adiabatic process. Step 3 is an adiabatic process. So no heat is lost. Okay, no heat is lost. Q is equal to 0. So we have to determine the change in internal energy during each step and work done during the adiabatic process. So let's understand. Before that, step 1 is basically from, let's say, initial state to another state. Step 2 is from another state to third state. And step 3, since step 3 is when it gets back to its normal condition. So it's from the third state to its initial state. Right, this is how. So it's again a cyclic process. Okay, so now this basically tests our knowledge of sign conventions as well as our knowledge of cyclic conditions. Okay, so over here, work is done on the system, work input. So W is equal to minus 50 joules. All right, Q is equal to heat is moving out. So Q is equal to minus 25 joules. Hence, using the first law, we'll get U is equal to, we'll get dQ is equal to du plus dw. Hence, delta U, change in internal energy during A to B, is going to be dQ minus dw. So Q is basically minus 25 and dw is basically 50, minus 50. So minus 50. So it's going to be 25 joules. All right. Delta U in A to B is plus 25 joules. Okay. Then let's talk about this. So over here, work done is 0. Heat is added, so it is plus 75 joules. And for a constant volume process, you know that dQ is equal to du. Hence, delta U is again plus 75 joules. So delta U for B to C is going to be plus 75 joules. Now, the third step we don't know, work done, we don't know internal energy. So over here, we are going to use the concept behind a cyclic process. For a cyclic process, integral du, cyclic integral of du is going to be 0, which implies delta U from A to B plus delta U from B to C plus delta U from C to A is going to be 0. So delta U from A to B we have as plus 25. And delta U from B to C we have 75 joules plus 75 joules plus delta U from C to A is 0. Therefore, you get delta U from C to A as minus 100 joules. Correct, minus 100 joules. So delta U from C to A is minus 100 joules. Okay, now we are going to use the first law. dQ is equal to du plus dw. So dw is going to be equal to minus du, which is minus of minus 100, which is plus 100 joules. Now it's plus 100. That means work is done by the system. Since work is done by the system, therefore work is released. Work out is positive. So work is 100 joules. All right. So this is basically my overall process. All right. So this really didn't need a PV diagram, but if you actually want to draw a PV diagram, a rough PV diagram for an analysis, then we can even draw rough PV diagram for this kind of process. So we can have this as my P, this is my V. So first of all, a constant pressure process where it receives 50 joules of work. So from here it goes in a straight line, a straight horizontal line. So a rough, so A to B is going to be something like this. Then B to C is a constant volume process where it receives heat. So when it receives heat, it's going to expand. It's a constant volume process. So therefore, its pressure is going to increase, right? Its pressure is going to increase because it is receiving heat. Remember, it is receiving heat. Therefore, its pressure would increase. Let me draw it properly. Whenever it would receive heat, it would tend to increase the temperature. And when its temperature would increase, then its pressure would increase. P is proportional to T at constant volume, right? So therefore, from A to B, it is going to move like this. So in A to B, or let's take it that way. Since it's moving from A to B, its internal energy increases, which means its temperature increases. Now at constant pressure with increase in temperature, the pressure would also increase. At constant pressure with increase in temperature, the volume would increase. So volume increases from A to B, right? Then in the second step, B to C, again internal energy is positive. That means temperature is increasing. So at constant volume, with increase in temperature, pressure would increase, right? So it will move somewhere here. And then the third one is, of course, an adiabatic process. So it's going to be something like this. Okay, something like this, it would fall. Okay, so this is going to be a rough PV diagram, although you don't require it as such for this kind of a question, but still, yeah, it can help. All right, so this was the problem that we had discussed. So these were the three important problems that we have discussed based on thermodynamic processes. So now we'll introduce the next term, which is enthalpy. It's a very important term. So basic definition of enthalpy is basically heat content of a system. Okay, heat content of a system. All right. So it can be mathematically expressed as sum of internal energy plus pressure into volume. All right, plus P into V. So from here you'll get dH is equal to du plus bdv plus vd. All right, pdv plus vdp. If we maintain pressure constant, then vdp is going to become 0. Therefore, we'll have dH is equal to du plus pdv. Since pressure is constant, therefore you will have dW is equal to pdV, or pdV is basically dW. So dH is equal to du plus dW. And by first law of thermodynamics, you have dQ is equal to du plus dW. Therefore, you will get dH is equal to dQ. Right? This is what we discussed. Right? Now, if you remember, for heat, we said that heat is basically heat capacity into dt. Right? Now, since here we have maintained constant pressure, therefore dq at constant pressure is going to be heat capacity at constant pressure into dt. And from here we have got dH is equal to dq. Therefore, we'll get dH is equal to Cp dt. Again, it depends only on temperature. Hence, it is a state property. It is a state property. Okay. So now dH is equal to dq at constant pressure. Hence, it becomes Cp into dt. All right. So now, using the same logic, we have dq equals to du plus dw, and dw is equal to pdv. Right. So if we keep volume constant, then we are going to get du is equal to dq. Right. Du is equal to dq, which gives us du is equal to cv dt. Same logic. Just like we have c dt, so at constant volume, it will become cv dt. Right. So we can write du is equal to cv dt. So these two are universal rules for ideal gases at constant, for a reversible process. du is equal to cv dt and dH is equal to cp dt. And also, you should remember that for an ideal gas, Cp minus Cv is equal to R. Cp minus Cv is equal to R. So this is this can be very easily derived. We will not go on to the derivation for now. All right. We'll just go with the concepts. All right. So that's quite important. So this was about enthalpy. So this is a very important term that we have introduced over here. All right. So in the next lecture, we'll be dealing with first law for flow processes. So in that case, enthalpy plays a very important role. So you should know what it mathematically means, how can we represent enthalpy mathematically, and what all different relations we can use. So make sure that these concepts of thermodynamics, these formulas of thermodynamics that we are dealing with, you should be very clear with these formulas. Just go through these formulas one by one and try to keep them in mind. Because after a few more lectures, you will find a number of formulas for thermodynamics. All right, a number of formulas, a number of concepts. So make sure that whatever you're learning, you are clear with all that. All right, you're clear with all that so that further it's easier for you to handle the subject. Otherwise, this subject is so vast, it is so manipulative, so complicated that you might get confused over here. All right. So it is one of the most complicated chemical engineering subjects. So make sure that you're clear, you have a tight grip over your concepts, you have crystal clear concepts while you're dealing with thermodynamics.